Look up at the night sky. What do you see? Pinpricks of light, distant worlds, the vast unknown stretching beyond imagination. For centuries, humans have gazed upward, searching for answers in the cosmos, and every discovery has rewritten our story. From Galileo's telescope revealing Jupiter's moons to the Hubble Deep Field exposing thousands of galaxies in a single frame, space has always been the ultimate classroom. But right now, we're living through something extraordinary, a golden age of cosmic breakthroughs that aren't just expanding our knowledge, they're poised to transform life on Earth in ways we're only beginning to grasp. Think about it, the same mysteries that once belonged to philosophers and poets are now unraveling before our eyes. Black holes humming gravitational waves, exoplanets with atmospheres that hint at alien life, minerals forged in supernova that could revolutionize medicine. These aren't just headlines, they're seismic shifts, each one a thread in a tapestry that could redefine humanity's future. And here's the breathtaking part, 30 of these discoveries, made within just the past few years, hold the power to alter everything from the tech in your pocket to the air you breathe. So what if I told you the key to curing diseases might be hiding in Martian soil, or that a distant star's explosive death could unlock limitless clean energy? This is the frontier we're exploring today, not as passive observers, but as active participants in a cosmic revolution. From mind-bending quantum phenomena in the vacuum of space to ancient asteroids carrying the building blocks of life, the universe is whispering secrets that could reshape our world. Buckle up, we're about to dive into 30 space discoveries so profound, they won't just change how you see the stars, they'll change how you see your own existence. Imagine stepping onto the rusty surface of Mars, not as a barren wasteland, but as a world hiding secrets beneath its dusty veil. For years, scientists debated whether liquid water could exist on the red planet, but now we know it's not just possible, it's real. Satellite after satellite has beamed back undeniable proof. Vast reservoirs of liquid water lurk beneath Mars' icy poles, buried over a kilometer deep. The European Space Agency's Mars Express orbiter first detected these hidden lakes using radar echoes, spotting a 20-kilometer-wide body of water near the South Pole. Then NASA Mars Reconnaissance Orbiter backed it up with even more evidence, revealing not just one but multiple subsurface lakes, kept liquid by salts that lower the freezing point. This changes everything. Water isn't just a resource, it's the foundation of life as we know it. If microbes evolved on Mars billions of years ago when rivers carved its canyons, their descendants could still be clinging on in those dark, briny depths. Suddenly, the hunt for alien life isn't about digging up fossils, it's about finding living organisms in an underground oasis. And for future colonists, these reservoirs could mean survival. Imagine melting ice for drinking water, splitting it into oxygen to breathe and hydrogen to fuel rockets. Mars just went from a distant dream to a tangible destination. But here's what really bends the mind. These lakes might not be alone. Some researchers suspect warmer volcanic regions could host even more liquid water closer to the surface, turning Mars into a patchwork of hidden wet zones. Every new discovery peels back another layer, proving the red planet is far from dead. It's a world waiting to be unlocked, and we're just beginning to read its story. Forget everything you thought you knew about distant worlds. The James Webb Space Telescope just tore up the old rulebook. Picture a planet 8.6 times heavier than Earth, orbiting a cool red dwarf star 110 light-years away. K2-18b looks nothing like the rocky worlds in our solar system. It's a Hycean planet, a swirling globe of hot oceans beneath a thick hydrogen atmosphere. But here's what set scientists' hearts racing. When Webb trained its golden eye on this alien world, it didn't just spot water vapor, it found carbon dioxide and methane and dimethyl sulfide, that last molecule on Earth. It's only produced by living organisms. This isn't just about one strange world. Webb's infrared vision has become our universal life detector, sniffing out chemical cocktails in exoplanet atmospheres across the galaxy. Take that carbon dioxide reading. It's the first definitive detection of the gas on a habitable zone planet. That's huge because CO2 acts like a planetary thermostat. Too much and you get a runaway greenhouse effect like Venus. Just enough, you've got the stable climate life needs to thrive. And the methane, it could be bubbling up from hydrothermal vents on the ocean floor, just like in Earth's earliest ecosystems. Now consider the implications. If dimethyl sulfide really is floating in K2-18b's air, we might be looking at an alien biosphere right now. Not fossilized microbes, not subtle hints, actual living chemistry happening right this second around another star. That changes the Fermi paradox math overnight. Maybe life isn't rare at all, just waiting for tools like Webb to reveal it. But there's another twist hiding in these atmospheric fingerprints. Every whiff of an exoplanet's air teaches us how to build future generation ships, a self-sustaining arcs that could carry humans between stars. Want to farm on a centuries-long voyage? Study how these alien atmospheres recycle gases. Need to mine raw materials from gas giants. Webb's showing us which molecules collect where. The same data hunting for aliens might one day keep interstellar colonists alive. Suddenly, those twinkling lights aren't just stars, they're beachheads. Each with worlds that could harbor life or someday us. Webb's peeling back the cosmic curtain, and what's behind it could redefine our place in the universe. Jupiter's moon, Europa, has long been the crown jewel of astrobiology, a frozen world with an ocean twice the volume of Earth's, sealed beneath an icy shell 15 miles thick. Scientists dreamed of sampling that hidden sea but faced an impossible hurdle: how to reach it. Then Hubble changed the game. Peering across 780 million kilometers, the telescope caught something astonishing: gigantic geysers erupting from Europa's south pole, spewing water vapor 100 kilometers into space. These aren't just cracks in the ice, they're fire hoses blasting direct samples of the subsurface ocean into the void. The implications are staggering. Instead of designing a nuclear-powered drill to tunnel through Europa's frozen crust, we could simply fly a spacecraft through these plumes and catch droplets of alien seawater. Imagine analyzing that material for microbial life or organic molecules without ever landing. NASA's upcoming Europa Clipper mission is designed to do exactly that, equipped with mass spectrometers to sniff the chemistry of these eruptions as it zooms past. But why does Europa have plumes at all? The answer lies in Jupiter's gravitational grip. As the moon orbits, tidal forces flex its icy shell, generating enough heat to keep the ocean liquid. That same squeezing likely fractures the ice, creating pathways for water to erupt. Some researchers think these plumes might even connect to hydrothermal vents on the ocean floor, the very environments where life could thrive without sunlight, powered by chemical energy alone. Here's what makes Europa's plumes even more tantalizing: they're unpredictable. Hubble has spotted them intermittently since 2012, suggesting they operate on cycles we don't yet understand. One theory: they might erupt when tidal stresses peak during Europa's elliptical orbit. That variability adds urgency. If we want to study them, we need to be watching at the right moment. And the discoveries don't stop at Europa. Similar plumes have been spotted on Saturn's moon Enceladus, proving this isn't a fluke but a phenomenon that could unlock oceans across the solar system. Each erupting geyser is like a cosmic vending machine, offering free samples of alien habitats. For the first time in history, we're not just searching for life, we're within reach of tasting it. Picture a world where bank transfers, military communications, even your private messages are utterly unhackable, not because of better firewalls, but because the laws of physics themselves guard the data. That future isn't science fiction anymore, thanks to a breakthrough 700 kilometers above Earth. China's Misha satellite, named after an ancient philosopher, didn't just send messages into space, it harnessed the bizarre rules of quantum mechanics to create the first unbreakable encryption key. Here's how it defied logic: by firing pairs of entangled photons toward ground stations 1,200 kilometers apart. MISHUS proved that particles could share a bond so intimate, any attempt to spy on them would instantly corrupt the data. No supercomputer could crack this code because quantum physics doesn't allow copying or intercepting without leaving a glaring fingerprint. But why does this matter beyond theoretical experiments? Think of the Internet's backbone: fiber optic cables buried under oceans, pulsing with trillions in financial transactions and state secrets. Today, hackers siphon data from these lines like thieves tapping phone wires. Quantum encryption changes the game entirely. MISHUS's successor satellites could weave an orbital web by 2040, linking continents through space-based relays where photons travel unimpeded by atmosphere at night. A bank in Tokyo could swap unstealable keys with a partner in London, while governments share intelligence with zero fear of leaks. Even your medical records, currently vulnerable in cloud servers, would become as secure as the universe's fundamental laws. The real magic lies in entanglement's spooky action at a distance, as Einstein called it. When two photons entangle, they mirror each other's properties instantaneously, whether separated by a millimeter or a galaxy. MISHUS exploited this by beaming one photon to Beijing and its twin to Vienna, then using their synchronized states to generate identical encryption keys. Any eavesdropper's presence would disturb the photon's delicate dance, triggering alarms. It's like sealing a letter with wax that shatters if touched, except the wax is subatomic particles obeying quantum rules no hacker can bypass. Yet challenges remain. Cloud cover absorbs photons, limiting transmissions to clear nights, and current quantum keys can't outpace conventional data speeds. That's where next-gen satellites come in. Imagine constellations of quantum relays hopping entangled photons between orbits to maintain global coverage. Europe's Quantum Communication Infrastructure Initiative already plans to loft its own satellites, while the US races to deploy quantum-resistant networks before adversaries catch up. This isn't just an arms race, it's a rewrite of cybersecurity's DNA, with space as the ultimate high ground. So the next time you hear about a data breach, remember, the solution might be soaring overhead, harnessing quantum weirdness to turn the heavens into a vault. MISHUS was the first whisper of a revolution, one where privacy isn't just protected, but guaranteed by the fabric of reality itself. Deep in the void between stars, humanity's ships face a terrifying problem: no GPS. Out there, the familiar constellations blur into meaningless patterns, and Earth's navigation signals fade to silence. But NASA found an ingenious solution, not by building a bigger antenna, but by listening to the universe's most precise clocks. Meet NISA, the International Space Station's unassuming suitcase-sized instrument that's rewriting the rules of cosmic travel by locking onto pulsars, the spinning corpses of dead stars. These aren't just celestial oddities, they're nature's atomic clocks beaming X-ray pulses with such regularity, they make Swiss watches look sloppy. Imagine a lighthouse, but one that spins hundreds of times per second, shooting beams of radiation so predictable you could set your watch by them for millennia. That's a pulsar. When massive stars explode, their collapsed cores, no larger than Manhattan but denser than Mount Everest, become these whirling dynamos. NISA's breakthrough was realizing their pulses could serve as interstellar mile markers. By comparing arrival times of X-ray flashes from multiple pulsars, a spacecraft can triangulate its position anywhere in the galaxy with accuracy down to 5 kilometers, like celestial GPS with no subscription fee. Here's why this is revolutionary. Traditional deep space navigation relies on Earth-based radio signals that weaken over distance and take hours to reach probes like Voyager. But pulsar navigation lets ships steer themselves in real time, even near Pluto or beyond. Picture a Mars-bound crew correcting their course autonomously mid-journey, or a probe to Alpha Centauri knowing its exact location light years from home. No more waiting for signals from Houston, just our onboard computer crunching pulsar timestamps like a cosmic Uber app. The real magic lies in redundancy. Unlike GPS satellites that can fail, pulsars are indestructible landmarks scattered across the galaxy. NASA proved this by guiding the ISS's position using millisecond pulsar data in 2017, achieving accuracy rivaling ground-based systems. But the implications stretch further. Future colony ships could carry pulsar almanacs, ensuring no one gets lost between stars. Even more thrilling, some pulsars are so stable, their timing could detect gravitational waves distorting spacetime en route, turning navigation into groundbreaking science. Yet challenges remain. X-ray telescopes need precision engineering to catch these faint, rapid pulses, and interstellar dust can scatter signals. That's where next-gen detectors come in. Projects like the European Space Agency's Pulsar Nav aim to shrink these systems to smartphone size, making them standard on every spacecraft. Suddenly, the Milky Way's spinning graveyard of dead stars becomes a highway of luminous signposts and humanity's ticket to fearless exploration beyond the solar backyard. So next time you glance at Google Maps, remember, the ultimate navigation tool isn't in your phone, it's the universe itself ticking away with pulsar precision, ready to guide us home from the stars. Titan's thick orange haze hides more than just a frozen wasteland. It's a bubbling chemical factory cooking up molecules we never dreamed could exist. When NASA Cassini probe dove through Saturn's largest moon's atmosphere, its instruments caught traces of something extraordinary: vinyl cyanide. To most, it sounds like industrial solvent. To astrobiologists, it's the potential cornerstone of alien life unlike anything on Earth. This isn't just about finding familiar chemistry in space, it's about discovering an entirely new rulebook for biology. Picture this on Titan, where temperatures plunge to -180 degrees Celsius. Water is harder than granite. But methane and ethane flow in rivers and lakes, creating a mirror universe where these liquids play the role water does on Earth. For decades, scientists wondered, could life emerge in such frigid hydrocarbon seas? Vinyl cyanide answers with a resounding maybe. Here's why. When this molecule assembles in Titan's conditions, lab simulations show it spontaneously forms hollow spheres called azotosomes, structures eerily similar to the lipid membranes enclosing Earth cells. Except instead of needing water, these membranes thrive in liquid methane, potentially offering microscopic compartments where alien biochemistry could unfold. Cassini spotted enough vinyl cyanide floating in Titan's upper atmosphere to theoretically form over 10 million membrane-like structures per cubic centimeter in its largest sea, Ligeia Mare. That's not speculation, it's quantitative proof that Titan's environment actively produces building blocks for alternative life, and the chemistry gets wilder. Titan's constant cosmic ray bombardment and UV exposure trigger complex reactions in its nitrogen-rich air, generating compounds like hydrogen cyanide that could serve as precursors for more elaborate biomolecules. But here's the twist that reshapes how we define habitable. Earth life relies on water's unique properties, its ability to dissolve nutrients, facilitate chemical reactions, and maintain cellular structures. Titan's chemistry suggests life might exploit liquid methane's very different characteristics, like its ability to harbor non-polar molecules that water would reject. Imagine organisms with membranes flexible at cryogenic temperatures, or metabolisms powered by acetylene instead of glucose. It's not just about life adapting to extreme environments, but life arising from fundamentally different rules. The implications ripple outward. If Titan can brew prebiotic chemistry in its methane lakes, why not similar moons orbiting gas giants in other star systems? Suddenly, the galaxy's habitable zone expands beyond the Goldilocks region where liquid water exists. to include countless frozen worlds with their own exotic solvents. Future missions like Dragonfly NAS, a planned rotorcraft lander, will hunt for these membrane structures directly when it touches down in 2034, sampling Titan's dunes for chemical clues. What Cassini uncovered isn't just another space oddity, it's a doorway to reimagining life's universal potential. Titan forces us to ask, is biology a singular phenomenon tied to Earth-like conditions, or merely one expression of a deeper, more versatile cosmic pattern? As we peel back the layers of this orange-skied enigma, we may find that life thrives not just in our image, but in forms as alien as the chemistry that birthed them. Buried in the asteroid belt between Mars and Jupiter floats a metallic Everest Psyche 16, a 226-kilometer-wide hunk of nickel, iron, and gold worth an almost inconceivable $10,000 quadrillion. To put that mind-bending number in perspective, it's enough to give every person on Earth $130 billion. But this isn't just cosmic bling. It's a time capsule from the violent birth of our solar system, and NASA's upcoming Psyche mission aims to crack it open. What makes this asteroid so special? Unlike most space rocks made of ice and rubble, Psyche appears to be the exposed metallic core of a failed planet, a relic from the chaotic collisions that shaped our early solar system 4.5 billion years ago. Imagine Earth's own fiery nickel-iron heart, but ripped out and frozen in space. That's the treasure trove we're about to visit. When NASA's spacecraft arrives in 2029, its magnetic sensors and gamma-ray spectrometers will map Psyche's composition down to the atomic level, revealing whether it's truly the skeletal remains of a protoplanet's gutted interior. Here's where economics crash into astrophysics. Psyche's iron alone could supply global metal needs for millions of years, bypassing Earth's destructive mining practices. Platinum group metals lurking in its crust, used in everything from cancer drugs to hydrogen fuel cells, could become abundant overnight, but the real game-changer lies in space itself. Future astronauts could smelt Psyche's resources into radiation shielding, space station components, or even rocket fuel depots without hauling materials from Earth's gravity well. Suddenly, the dream of self-sustaining Martian colonies or lunar factories shifts from sci-fi to spreadsheet calculations, yet the challenges are as massive as the payoff. No one's ever mined in microgravity, where molten metal would float away in globules. Conventional drills would overheat without atmospheric cooling, and asteroid ore lacks the concentrated veins found in terrestrial mines. That's why companies like Astroforge are already testing prototypes, container-sized spacecraft that could vaporize metal-rich asteroids with focused sunlight, then condense the vapor into pure ingots. Others propose capturing smaller asteroids and parking them near the moon for processing, turning celestial bodies into orbiting warehouses. The legal landscape adds another layer. The Outer Space Treaty bans national claims on celestial bodies, but says nothing about private extraction. Luxembourg and the UAE have already passed laws letting companies keep what they mine, sparking a new space gold rush. Imagine a future where Wall Street tracks asteroid prospectors alongside oil futures, and off-world metals crash terrestrial commodity markets. A single successful haul could rewrite global trade, or trigger conflicts over who owns the solar system's riches. Psyche's value isn't just in its metals, but in the knowledge it holds. By studying this cosmic wreckage, we'll learn how planetary cores generate magnetic fields, the invisible shields that protect atmospheres and enable life. It's a chance to touch the building blocks of worlds, including our own. And perhaps in its reflection, we'll see not just dollar signs, but the blueprint for becoming an interplanetary civilization. The mission hasn't even launched, yet Psyche already challenges us to rethink scarcity, ownership, and our place in the cosmos. Gravity tugs at the cosmos with an invisible hand, but what if the force bending light around galaxies isn't coming from the stars we see? That's the enigma of dark matter, the universe's hidden skeleton making up 85% of all mass. For decades, it's been a ghost in the equations, detectable only by its gravitational fingerprints. Now, the Euclid Space Telescope is flipping on the lights. Launched in 2023, this European marvel isn't just spotting dark matter. It's constructing the most detailed 3D atlas of its distribution ever made, mapping its tendrils across 10 billion light-years like cosmic cartography. Euclid's method is as brilliant as it is indirect. By observing how light from distant galaxies warps as it passes through dark matter's gravitational field, an effect called weak gravitational lensing, the telescope traces the invisible. Imagine stretching a sheet of rubber and rolling marbles across it. Their paths bend where the sheet dips under unseen weights. Euclid does this on a galactic scale, plotting distortions in the shapes of millions of galaxies to reconstruct the dark matter scaffolding between them. Early results reveal a web far more intricate than simulations predicted, with filaments denser in some regions and shockingly sparse in others. Why does this matter beyond astrophysics? Dark matter's structure could hold keys to energy breakthroughs we've barely imagined. Some theorists speculate clusters might contain exotic particles that annihilate on contact, releasing pure energy, a potential power source orders of magnitude beyond nuclear fusion. Others suggest manipulating dark matter's gravitational effects might enable warp drive like propulsion, bending spacetime itself. While these ideas sound like sci-fi, remember, GPS relies on accounting for relativity's time warps, a once impractical Einsteinian quirk now in every smartphone. Euclid's maps might also solve a glaring puzzle: why the universe's expansion is accelerating. Dark matter's distribution could reveal if it's interacting with dark energy, that mysterious force ripping space apart. Picture it as a cosmic tug-of-war, dark matter's gravity pulling galaxies together while dark energy flings them apart. Understanding their balance could predict the universe's ultimate fate, a cold, scattered void or a cyclical rebirth. Yet the most tantalizing possibility is practical harvesting. If dark matter particles are as heavy as some models suggest, they could be concentrated in planetary gravity wells. Earth's core might hold reservoirs we could someday extract. Far-fetched, perhaps, but so was splitting the atom before we grasped quantum mechanics. Euclid's revelations are more than academic. They're the first steps toward mastering the universe's dominant yet elusive material. Every flicker of distorted starlight it records isn't just data, it's a clue to the invisible engine powering reality itself. Picture a spacecraft with no roaring engines, no fuel tanks, just a gossamer sheet thinner than plastic wrap, catching starlight like an interstellar windsurfer. That's the magic of Light Sail 2, the crowning achievement of solar sailing. Launched in 2019 by the Planetary Society, this breadbox-sized probe unfurled a 32-square-meter sail in Earth's orbit, proving sunlight alone could propel a vessel through space. Photons, those tiny packets of light energy, don't just illuminate your morning, they carry momentum. And when billions of them bounced off Light Sail's mirrored Mylar surface, they nudged the craft with enough force to raise its orbit by multiple kilometers. No chemical explosions, no thruster firings, just pure, silent momentum from starlight. Now imagine scaling this principle to a technology that could bridge the interstellar void. Breakthrough Starshot, backed by visionary Yuri Milner and Stephen Hawking's legacy, isn't aiming for modest orbit adjustments, their audacious plan. To fling a fleet of Gram-scale starships toward Alpha Centauri at 20% light speed, covering 4.37 light-years in just 20 years. The key, a 100-gigawatt array of Earth-based lasers firing at ultra-thin light sails no wider than a picnic blanket. These wouldn't be passive sunlight catchers like Light Sail, but vessels pushed by concentrated beams capable of accelerating them to 60,000 kilometers per second in mere minutes. The engineering hurdles are staggering. A sail that thin would vaporize if it absorbed even a fraction more energy than intended. navigation becomes a nightmare when maneuvering at relativistic speeds. How do you correct course when signals take 4 years to reach the probe? Yet the rewards eclipse the risks. Starshot's tiny probes, each carrying cameras and sensors, could beam back the first close-up images of an alien solar system's planets, scanning Proxima Centauri b for oceans or vegetation. This isn't just about reaching the stars, it's about doing so within a human lifetime, transforming interstellar travel from millennia-long odysseys to something approaching a commuter flight. Solar sailing also solves a problem plaguing deep space missions, the tyranny of the rocket equation. Traditional probes like Voyager carry finite fuel, limiting how much they can accelerate or change direction. But a solar sail's fuel tank is effectively infinite. As long as starlight or lasers keep pushing, the craft keeps accelerating. Japan's Ikaro's mission proved this in 2010, sailing past Venus using only sunlight. Future sails could ride laser beams to deliver supplies to Mars colonies or act as interstellar messaging relays, their sails doubling as antennas to ping data across light years. Here's where it gets even wilder. Advanced concepts propose sails made of atom-thin graphene or metamaterials that change reflectivity on demand, allowing steering without bulky thrusters. Others imagine solar wind sails catching not just light but charged particles streaming from stars, a double boost. The real breakthrough lies in sustainability. Unlike chemical rockets that litter orbit with debris, light sails leave no trace beyond their wake in the photon sea. Light Sail 2 may have been a modest prototype, but its legacy is cosmic. It proved that the gentle pressure of sunlight, a force so faint it's drowned out by a child's breath on Earth, can move mountains in the frictionless realm of space. And as we look toward the stars, these shimmering sails might just be humanity's ticket to touching them. The Martian air holds a mystery that's been tantalizing scientists for decades, fleeting puffs of methane gas that appear and vanish with the seasons. NASA Curiosity rover first sniffed out the gas in 2013, and the readings have followed a bizarrely predictable pattern ever since. Methane levels spike during the red planet's summer months, then plummet when temperatures drop. On Earth, 90% of atmospheric methane comes from living organisms, from burping cows to microbes in swamps. So when Curiosity's laser spectrometer caught whiffs of the gas inside Gale crater, sometimes as high as 21 parts per billion, the immediate question was unavoidable. Is Mars exhaling evidence of subterranean life? But here's where the plot thickens. Methane isn't just a biosignature, it can also be forged through purely geological processes. When water interacts with certain minerals like olivine in a process called serpentinization, or when ancient methane clathrates trapped in ice get exposed to sunlight, the gas can seep into the atmosphere. ESA's Trace Gas Orbiter initially failed to confirm Curiosity's methane spikes from orbit, deepening the debate. Some researchers argue the rover itself might be releasing trace methane, though NASA meticulously ruled this out by having Curiosity sample its own exhaust for comparison. Others propose the methane could be pooling near the surface at night and dispersing during daylight, creating localized bursts the orbiter misses, the most electrifying hypothesis. Mars might host methanogens microbes that metabolize hydrogen and carbon dioxide, exhaling methane as waste. On Earth, these extremophenes thrive in places like hydrothermal vents and deep underground oil reservoirs. If similar organisms exist beneath Mars' permafrost, shielded from radiation, their metabolic cycles could sync with seasonal temperature changes, becoming more active when subsurface ice briefly melts. Imagine microbial colonies lying dormant through the frigid Martian winter, then stirring to life when summer warmth trickles down, releasing gas as they feed. It's a captivating theory, but without drilling deeper than Curiosity's 6-centimeter soil samples, we're left with circumstantial evidence. Yet this isn't just an academic puzzle. Methane's seasonal ebb and flow could be the key to sustaining future human outposts. The gas is a potent rocket fuel ingredient when combined with liquid oxygen, precisely what SpaceX's Starship engines burn. If settlers can tap underground methane reservoirs, they'd have a ready-made propellant source instead of hauling fuel from Earth. Even more intriguing, genetically engineered bacteria could be deployed to ranch Martian methane, tweaked to optimize production for both breathing air and refueling needs. Synthetic biologists are already developing Earth-based microbes that convert CO2 into methane. The same tech might one day turn Martian soil into a biofuel factory. What makes these methane cycles so revolutionary isn't just the possibility of ancient life, it's the potential to harness them for humanity's next chapter. Whether the source is geological or biological, Mars is quietly offering up resources we'd be foolish to ignore. Every summer spike in Curiosity's data might be more than a scientific curiosity. It could be the red planet whispering instructions on how to survive there. For almost a century, astronomy relied on a single language: light. Telescopes decoded the universe by capturing photons across the spectrum, from radio waves to gamma rays. But in the pre-dawn hours of August 17, 2017, humanity gained an entirely new sense: hearing. That's when gravitational wave detectors LIGO and Virgo caught the faintest ripple in space-time, a vibration so minuscule it stretched a 4-kilometer-long laser beam by less than 1/10,000th the width of a proton. This wasn't just another black hole merger. The signal, catalogued as JWST, came from two neutron stars spiraling together 130 million light-years away, and it triggered the most coordinated astronomical observation in history. Within seconds of the detection, automated alerts lit up observatories worldwide. NASA Fermi satellite had already spotted a gamma ray burst from the same patch of sky just 2 seconds after the gravitational waves arrived. Within hours, optical telescopes swiveled toward the galaxy NGC 4993, where they found something never seen before: a kilonova, an explosion 1,000 times brighter than a typical nova, glowing from the radioactive decay of heavy elements forged in the neutron star collision's aftermath. For the first time, we weren't just watching the cosmos, we were witnessing an event through multiple cosmic messengers: gravitational waves, electromagnetic radiation, and even neutrinos. This was the dawn of multi-messenger astronomy, a revolution as profound as Galileo first pointing his telescope at Jupiter. The real breakthrough wasn't just confirming Einstein's century-old prediction that merging massive objects create space-time ripples. It was what the collision revealed about the universe's chemical factory. Spectroscopic analysis showed the kilonova's light carried the fingerprints of gold, platinum, and uranium. Proof that these precious metals aren't forged in supernova as once thought, but in these violent neutron star mergers. Suddenly, the wedding ring on your finger or the uranium powering nuclear reactors became relics of ancient cosmic cataclysms. Every heavy atom in our bodies likely traces back to similar collisions scattered across cosmic history. But the implications stretch beyond chemistry. Gravitational waves travel undisturbed through cosmic dust and gas, allowing us to probe regions opaque to light like the cores of supernova or the edge of black holes. Future detectors like ESA's planned LISA space-based observatory could catch mergers from the universe's first stars or even hypothetical cosmic strings left over from the Big Bang. Imagine combining gravitational wave data with neutrino detectors and next-gen telescopes. We're not just opening a new window on the universe, we're constructing an entire sensory suite to experience it in ways previously confined to theory. Perhaps most thrilling is the speed at which this field is evolving. JW170817's detection took 70 years of theoretical work and decades of technological refinement. Now, upgraded detectors spot neutron star mergers almost monthly, each one offering fresh clues about matter's behavior under extreme densities we could never replicate on Earth. Somewhere in those space-time tremors might lie answers to quantum gravity, dark matter, or the fate of neutron stars. Do they collapse into black holes or reveal exotic quark matter at their cores? That faint chirp in LIGO detectors didn't just mark the end of two neutron stars. It signaled the beginning of a new era where we don't just see the universe, but feel its vibrations, decode its elemental recipes, and trace the very fabric of reality itself. Venus was always the cautionary tale, a planetary sibling gone horrifically wrong, with surface temperatures hot enough to melt lead and skies raining sulfuric acid. That's why the scientific world reeled when researchers announced they'd spotted phosphine gas in Venus' upper atmosphere in 2020. On Earth, this foul-smelling molecule is almost exclusively produced by anaerobic bacteria thriving in oxygen-free environments like swamps and animal guts or in labs. Finding it floating 50 kilometers above Venus' surface was like detecting smoke and wondering if there might be fire. The discovery ignited a firestorm of debate because if phosphine really exists there, and if it's not from some unknown geological process, then we're left with one electrifying possibility. Microbial life could be floating in Venus clouds. Let's unpack why this is so revolutionary. Venus upper cloud decks hover around 30 degrees Celsius, downright cozy compared to the inferno below. The atmospheric pressure at that altitude is remarkably Earth-like, and while the droplets are sulfuric acid, extremophiles on Earth already thrive in similarly hostile places, like Yellowstone's acidic hot springs. But here's what bends the rules entirely. If life exists there, it wouldn't just expand the habitable zone, it would shatter it. Suddenly, a planet with surface conditions worse than a blast furnace enters the biological conversation, forcing us to ask whether life needs planetary surfaces at all. Could countless other worlds harbor life in their skies, untethered to rocks or oceans? The controversy lies in the detection itself. The original team, using the James Clerk Maxwell Telescope and ALMA, reported phosphine levels at 20 parts per billion, a tiny but persistent signal. Skeptics countered that the data might have been thrown off by sulfur dioxide, a common Venusian gas that absorbs radiation at similar wavelengths. Subsequent studies couldn't replicate the findings, and recalibrations of ALMA data reduced the phosphine levels to nearly undetectable. Yet the debate refuses to die because the stakes are too high. Even the faintest chance of aerial life has spurred NASA and ESA to fast-track missions like Da Vinci and Envision, which will probe Venus' atmosphere with precision instruments by the early 2030s. Beyond astrobiology, Venusian phosphine could revolutionize medicine. Earth's acid-loving microbes already produce compounds used in drugs like statins and immunosuppressants. If Venusian clouds host life, their biochemistry might yield exotic molecules evolved to stabilize proteins in sulfuric acid, a property that could lead to breakthroughs in drug delivery or industrial enzymes. Picture pharmaceuticals designed to survive the harsh acidity of the human stomach, or materials engineered to resist corrosion in extreme environments. What makes this discovery so tantalizing isn't just the question of whether it's real, it's how it forces us to rethink life's adaptability. If organisms can flourish inside acidic Venusian clouds, then the galaxy's habitable real estate just got a radical upgrade. Not every world needs oceans or temperate forests. Maybe life is everywhere, even in the unlikeliest corners, waiting for us to recognize it in forms we've barely begun to imagine. The human body wasn't designed for space. Muscles wither, bones weaken, even the heart changes shape without gravity's constant tug. But in this apparent adversity, scientists have stumbled upon something extraordinary. Weightlessness might hold the key to growing perfect human organs on demand. Aboard the International Space Station, researchers have watched stem cells perform what seems like magic, assembling themselves into intricate three-dimensional organoids, structures that mimic hearts, livers, and kidneys with startling precision. On Earth, these same cells collapse into flat, dysfunctional clumps, but released from gravity's grip, they self-organize as if following some primordial blueprint, layering themselves into complex tissues with blood vessels and chambers that pulse with rhythmic contractions. What makes microgravity so transformative? On the ground, attempting to bioprint organs feels like building a house during an earthquake. Gravity distorts delicate cellular scaffolding before it can solidify. But in orbit, tissues form without compression, allowing layers to fuse naturally. NASA biofabrication facility, installed on the ISS in 2019, has already printed test patches of cardiac tissue that beat in synchrony, while private ventures like Lambda Vision grow artificial retinas layer by layer in orbit. The implications are staggering. Imagine warehouses in low Earth orbit stocked with lab-grown lungs, kidneys, or pancreatic islets, ready for transplant with zero rejection risk because they're grown from the patient's own cells. The real breakthrough lies in scalability. Current Earth-based organoid research produces tissues the size of peas, useful for drug testing but too small for transplants. Space-grown constructs, however, show potential to reach full size. In 2022, a University of Zurich experiment sent adult stem cells to the ISS and returned with millimeter-thick muscle strands, 10 times thicker than anything cultured on Earth. This isn't just about thickness. Microgravity allows nutrients and oxygen to diffuse evenly through developing tissues, preventing the necrotic cores that plague large lab-grown structures. But the road ahead isn't without hurdles. Astronauts can't spend hours tending fragile organ cultures between spacewalks, so automated bioreactors are critical. Companies like Space Tango deploy suitcase-sized labs that remotely monitor cell growth, adjusting temperature and nutrient flow from ground control. Then there's the challenge of returning these delicate structures safely through Earth's atmosphere, a problem inspiring wild solutions like embedding organs in temperature-stable gels or even printing protective shells around them during descent. Looking toward 2050, the vision becomes even more audacious. Picture orbital facilities where 3D bioprinters coordinate with stem cell banks, guided by artificial intelligence that tailors each organ to the recipient's DNA. Need a new liver? Your doctor uploads your scan, and a custom organ grows in weeks, not years. This could erase transplant waitlists that claim 30 lives daily in the US alone. Yet the greatest impact might be in unexpected places. Pharmaceutical companies are racing to use space-grown organoids for drug testing, creating miniature human livers or brains that respond to medications more accurately than animal models. It's a sobering thought. The same environment that damages astronauts' bodies might soon mass-produce the very tissues that heal ours. The cosmos, it seems, isn't just a frontier to explore. It's a workshop where biology's most complex puzzles assemble themselves, if only we learn to listen to gravity's absence. The night sky holds countless secrets, but in 2017, astronomers spotted something stranger than fiction. Hurtling past Earth at 87 kilometers per second, a bizarre cigar-shaped object tumbled end over end, reflecting sunlight 10 times more intensely than typical comets. This was Oumuamua, our first confirmed interstellar visitor, and its peculiarities sparked debates that still rage today. Unlike solar system comets with their fuzzy tails, Oumuamua showed no outgassing when closest to the Sun, yet mysteriously accelerated as if pushed by an unseen force. Some researchers proposed exotic explanations, from hydrogen icebergs vaporizing invisibly to, more controversially, artificial origins like a light sail fragment from an alien civilization. While most scientists favor natural explanations, one truth became undeniable. The cosmos is far more restless than we imagined, with interstellar traffic passing through our neighborhood all the time. Just 2 years later, another traveler arrived, Comet Borisov, this time unmistakably icy with a classic tail. Where Oumuamua was dry and rocky, Borisov's water-rich composition mirrored comets from our own solar system, hinting that the ingredients for life might be common currency among stars. But what made both visitors revolutionary wasn't just their origins. It was how they forced us to rewrite the rules. Traditional telescopes almost missed Oumuamua entirely because its elongated shape and rapid rotation didn't match any known asteroid or comet models. Now, next-gen observatories like the Vera-Rubin telescope are being reprogrammed to spot these cosmic drifters earlier, giving us precious months instead of days to study them. Consider the implications. If interstellar objects pass through regularly, current estimates suggest at least one per year within Jupiter's orbit. They could be galactic library cards carrying materials from distant star systems. Oumuamua's possible nitrogen ice might hold clues about exoplanet atmospheres, while Borisov's organic molecules might reveal whether the building blocks of life are universal. Future missions could rendezvous with these travelers, sampling them like interstellar pollen to compare chemistry across the galaxy. Yet the real game-changer lies in what we might one day catch. Statistically, some interstellar objects could be fragments of shattered exoplanets, even carrying fossilized microbes from alien oceans. Others might be artifacts of ancient spacefaring civilizations, discarded probes or accidental debris now adrift between stars. Projects like the Galileo Initiative are designing specialized instruments to identify such anomalies, scanning for materials with unnatural isotopic ratios or geometries that defy erosion. These visitors remind us that we're not just observers of the cosmos, we're participants in an endless exchange of matter and potential life. Every unusual acceleration, every unexpected chemical signature, is a puzzle piece in understanding whether life on Earth is a singular accident or part of a vast, interconnected tapestry. The next time an interstellar wanderer appears, we'll be ready, not just with telescopes, but with probes poised to intercept, because the universe's greatest stories might arrive unannounced, riding silent on the solar wind. For centuries, black holes existed only as equations in Einstein's theory of relativity, mathematical monsters so dense, not even light could escape their grip. Then, in April 2019, humanity peeled back the veil. The Event Horizon Telescope collaboration unveiled something unprecedented, a fiery ring of light surrounding the pitch-black shadow of M87's supermassive black hole, 55 million light-years away. This wasn't just an image, it was a triumph of cosmic-scale engineering. 8 radio telescopes spanning from Hawaii to the South Pole synchronized their observations with atomic clocks, effectively creating a virtual dish as wide as Earth itself, capable of spotting a donut on the Moon's surface. What makes this photo revolutionary isn't just the visual confirmation of black holes. The glowing ring reveals the accretion disk, a maelstrom of superheated plasma spiraling near light speed before vanishing into oblivion. Studying these disks could rewrite physics textbooks. The temperatures here reach billions of degrees, and magnetic fields twist into ropes stronger than anything we can generate in labs. Some theorists believe these conditions might produce phenomena we've only dreamed of, like negative energy particles that could stabilize wormholes or mechanisms for extracting black hole spin energy. Now imagine harnessing a fraction of that power. The energy efficiency of accretion disks dwarfs anything in human experience. Nuclear fusion converts about 0.7% of mass into energy. Black hole accretion can hit 40%. That's why futurists like physicist Roger Penrose envision Penrose spheres, megastructures surrounding black holes to capture this energy via relativistic particle beams. Practical, not yet, but neither were nuclear reactors when Einstein penned E=mc². The real breakthrough lies in the details. M87's black hole didn't just match predictions, it challenged them. The ring's asymmetry hints at plasma dynamics we don't fully understand, possibly involving magnetic reconnection events that outshine entire galaxies. Similar processes might explain fast radio bursts or even dark matter interactions. Upgraded telescopes, including space-based ones, could soon track how these disks evolve in real time, offering front-row seats to spacetime's most violent ballet. Here's where it gets even wilder. Some accretion disks emit coherent light laser-like beams that could theoretically transmit information across the universe. Others spit out jets of matter moving at 99% light speed, cosmic particle accelerators far beyond anything at CERN. If we decode how these natural engines work, we might replicate their efficiency for clean energy or propulsion. Picture spacecraft riding black hole-powered jets to the stars, or cities lit by miniature accretion reactors. The Event Horizon Telescope didn't just snap a historic photo, it opened a doorway to physics' next frontier. Every flicker in that fiery ring carries secrets about gravity's extremes, matter's limits, and perhaps even new energy paradigms. As we stare into that darkness, we're not just seeing a black hole's shadow, we're glimpsing the future of human ingenuity, written in the swirling light of the impossible. The moon's shadowed craters hide more than eternal darkness, they're cosmic freezers packed with ice, and NASA's lunar flashlight mission just revealed their most accessible deposits yet. Picture a world where water doesn't flow in rivers but lingers as frost in abyssal pits where sunlight never reaches. For decades, radar hints and impact probe data suggested these frozen caches existed, but it took a shoebox-sized spacecraft equipped with lasers to map them with precision. Lunar Flashlight didn't just detect ice, it pinpointed surface frost in craters like Shackleton at the moon's south pole, proving water isn't buried deep but scattered like glittering crumbs waiting to be harvested. What makes this revolutionary isn't just the presence of water, it's the practicality. Unlike Mars's deep aquifers or Titan's methane lakes, lunar ice sits in superficial layers, some just microns thick. Solar-powered robots could scrape it up with minimal energy, then split it via electrolysis into oxygen for breathing and hydrogen for fuel. Suddenly, the moon transforms from a barren stopover into a galactic gas station. A single ton of lunar water converted to rocket propellant could launch missions to Mars for a fraction of Earth's costs, bypassing the tyranny of our planet's gravity well. The economics are staggering. Launching 1 kilogram of water from Earth costs roughly $20,000. Harvesting it on-site, pennies. NASA's Artemis program already plans to land astronauts near these icy reserves by 2026, with companies like SpaceX and Blue Origin designing ice mining rovers. Imagine bulldozers with thermal drills vaporizing frost into capture chambers, or reflective mirrors concentrating sunlight into shadowed craters to sublimate ice directly into pipelines. This isn't science fiction, it's logistics planning happening right now. But the real breakthrough lies in sustainability. Water isn't just for drinking or fuel, it's radiation shielding. Moon settlers could surround habitats with ice-filled walls, blocking cosmic rays without hauling heavy metals from Earth. Agriculturists propose hydroponic farms where lunar water nourishes crops under domes, while chemists eye it as feedstock for manufacturing plastics or ceramics. The moon could become a workshop where raw materials are processed into spacecraft parts, then launched effortlessly in the weak gravity. Yet the most tantalizing possibility isn't just using the ice, it's decoding its origins. Comet impacts likely delivered much of this water billions of years ago, meaning lunar frost might preserve ancient organic molecules from the early solar system. By studying its isotopic ratios, we could trace Earth's own water history. Did our oceans come from similar cosmic deliveries? Lunar Flashlight's maps are the first step toward answering these questions, turning the moon into both a resource depot and a time capsule. Every speck of ice in those craters represents more than survival, it's the key to thriving beyond Earth. With each laser ping from orbit, we're not just locating water, we're charting the blueprint for humanity's first permanent outpost among the stars. The moon is no longer a destination, it's a foundation, and the ice clinging to its shadows is the mortar that will build our future. Most stars drift through the galaxy at a leisurely pace, bound by gravity's embrace, but a handful are cosmic fugitives, hurtling through space so fast they're escaping the Milky Way entirely. The Gaia Space Telescope recently spotted dozens of these hypervelocity stars, some rocketing away at over 2 million miles per hour, speed so extreme they could cross the distance between New York and Los Angeles in under 5 seconds. These aren't just celestial oddities, they're cosmic breadcrumbs tracing paths that could lead us to invisible dark matter or even guide future interstellar travelers. So where do these stellar speed demons come from? The leading theory involves the supermassive black hole at our galaxy's heart. When a binary star system wanders too close to Sagittarius A, one star may get captured while the other is violently slingshot outward like a stone from a sling. Gaia's precise velocity measurements confirm some hypervelocity stars originate near the galactic center, their trajectories pointing back like arrows to the scene of their ejection. But others defy explanation. Their speeds suggest encounters with something even more exotic, like clusters of dark matter or ancient collisions between galaxies. Here's where these rogue stars become cosmic cartographers. As they streak through the Milky Way's halo, their paths subtly bend under the influence of invisible mass at dark matter's gravitational pull. By tracking these deviations, astronomers can map the distribution of dark matter with unprecedented precision, turning each hypervelocity star into a probe of the unseen. It's like watching leaves caught in a river's current to deduce the shape of hidden rocks below. Already, Gaia's data hints at dark matter clumps where none were predicted, potentially rewriting our understanding of the galaxy's hidden skeleton. But the implications stretch beyond astrophysics. Hypervelocity stars could serve as interstellar lighthouses for future voyages. Imagine a spacecraft navigating by these ultra-fast beacons, their fixed trajectories unaffected by the chaotic motions of slower stars. A voyage to Alpha Centauri might use a hypervelocity star's consistent path as a reference point, correcting course mid-journey with pinpoint accuracy. Some of these stars are even headed toward neighboring galaxies. In billions of years, they could carry unintended passengers, microbes, or human artifacts across the cosmic void. What's truly staggering is the energy behind these ejections. The force required to accelerate a star to such velocities rivals supernova explosions, yet leaves the star intact. Studying their survival could reveal secrets about stellar structure, perhaps inspiring new ways to shield ships from extreme acceleration. Others speculate these stars might harbor planets, though any survivors would be frozen worlds in perpetual exodus, lit only by the fading glow of their runaway suns. In the grandest perspective, hypervelocity stars remind us the galaxy is anything but static. It's a dynamic arena of gravitational pinball, where stars become both pawns and probes in a game we're just beginning to understand. Every new trajectory Gaia records isn't just a data point, it's a thread in the tapestry of forces shaping the cosmos, and perhaps humanity's future roadmap to the stars. Deep beneath the Antarctic ice, where temperatures plunge to -60 degrees and the pressure could crush a submarine, lies humanity's most unusual telescope ice cube. Unlike traditional observatories that gather light, this colossal detector hunts for ghostly particles called neutrinos, which streak through the cosmos nearly untouched by matter. These subatomic phantoms are so elusive that trillions pass through your body every second without a single collision. Yet in 2018, IceCube achieved the impossible. It traced a single high-energy neutrino back to a blazar 4 billion light-years away, a supermassive black hole spewing jets of radiation directly at Earth. This wasn't just a cosmic coincidence, it was proof that the universe is teeming with natural particle accelerators, churning out neutrinos like interstellar Morse code. What makes neutrinos revolutionary isn't just their origin story. It's how they could rewrite the rules of communication. Light gets blocked by planets, absorbed by dust, or distorted by magnetic fields, but neutrinos pierce through everything. Imagine sending a message that tunnels straight through Earth's core to the other side without towers or satellites, or transmitting data across a galaxy thick with nebular debris that would scramble radio waves. A neutrino-based system could do all this, making them the ultimate interstellar couriers. Even more tantalizing, quantum information suffers from decoherence when transmitted via photons, but neutrinos' weak interactions might preserve quantum states across cosmic distances, potentially enabling unhackable quantum communication networks spanning solar systems. The challenge has always been detecting these shadowy particles, but IceCube's design is sheer genius. Its sensors are frozen into a cubic kilometer of clear ice, waiting for the rare moment a neutrino collides with an atom and creates a flash of blue Cherenkov radiation. Tracking these flashes lets scientists reconstruct the neutrino's path back to its source like cosmic forensics. That blazar detection proved neutrinos can carry directional information from the farthest reaches of space, encoded in their energy and trajectory. Now, researchers are working on miniaturized versions of this tech tabletop neutrino detectors that could one day fit aboard spacecraft, turning these particles into a universal positioning system for navigating the void. Here's where it gets wilder. Some theorists propose that advanced civilizations might already be using neutrinos for communication, their signals hiding in plain sight amidst the natural background flux. Projects like ANITA, a balloon-borne antenna array circling Antarctica, are scanning for anomalous neutrino patterns that could hint at artificial origins. Meanwhile, physicists at Fermilab are experimenting with neutrino beams to send messages through solid rock, achieving data transmission where conventional signals fail, like mines or submarines. The US Navy even holds patents for neutrino-based submarine comms, hinting at military applications, yet the true promise lies in fundamental science. Every high-energy neutrino is a messenger from environments we can't otherwise probe: the swirling disks of black holes, the hearts of supernova, or perhaps even the decay of dark matter. IceCube's successor, IceCube Gen 2, will expand the detector's volume tenfold, turning Antarctica into a neutrino sieve that could catch particles from the dawn of time. We're on the verge of a paradigm shift where these cosmic specters aren't just observed but harnessed, threading the galaxy with an invisible web of information. The universe has been whispering in neutrinos for billions of years. We're finally learning to listen. High above the Earth, where sunlight never dims behind clouds or fades with nightfall, a quiet revolution is unfolding, one that could rewrite the rules of clean energy by mid-century. Earlier this year, Caltech's Space Solar Power Demonstrator, or SSPD-1, achieved what once sounded like science fiction. It successfully beamed solar energy harvested in orbit down to our planet's surface without a single wire. This wasn't just a lab experiment, it was the first concrete proof that space-based solar power could work at scale, transmitting electricity across the void as precisely as a laser beam scans a barcode. The genius lies in the engineering. Unlike terrestrial solar panels shackled to daylight hours and weather patterns, orbital arrays soak up unfiltered sunlight 24/7, with intensities up to 10 times stronger than on Earth's surface. SSPD-1 breakthrough was miniaturizing the key components: ultra-lightweight photovoltaic cells thinner than a human hair, paired with modular tiles that convert direct current into microwave beams. These microwaves, harmless radio frequencies similar to Wi-Fi but far more focused, were then aimed at a receiver array on campus, where they were reconverted into electricity with startling efficiency. While the test transmitted only a tiny fraction of the energy needed to power a light bulb, it proved the physics scales. Future iterations could beam gigawatts from geostationary orbit, equivalent to multiple nuclear plants operating around the clock. Critics once dismissed the concept as fantasy, citing the colossal costs of launching solar farms into space. but plummeting rocket prices driven by SpaceX's reusable Falcon boosters and Starship prototypes have slashed the math. A single Starship launch could deploy football field-sized arrays for a fraction of traditional energy infrastructure costs. The real game changer, these orbital power stations could deliver energy anywhere on Earth at the speed of light. No pipelines, no political borders, just clean electricity zapped to disaster zones, remote mines, or forward military bases on demand. Imagine hurricane-ravaged cities bypassing months of grid repairs by deploying temporary receivers to catch power from orbit, or developing nations leapfrogging fossil fuels entirely with space-beamed energy. The environmental upside is staggering. Unlike terrestrial renewables that require vast tracts of land, solar farms covering deserts or wind turbines dotting coastlines, space-based arrays occupy the ultimate empty lot, high orbit, where they cast negligible shadows on Earth. And while the microwave beams sound ominous, they're designed to diffuse at intensities safer than sunlight, with automatic shutdowns if the beam drifts off target. Scaling this tech could slash global carbon emissions by a third by 2060, all while providing baseload power that outshines intermittent ground-based renewables. Yet the path forward isn't without hurdles. Maintaining and repairing arrays in the harsh radiation of space will require autonomous robots or astronaut crews, adding complexity. There's also the lingering challenge of energy storage. While space solar solves generation, we'll still need better batteries for nighttime distribution. But with Japan and the European Space Agency already testing their own prototypes, and the US Department of Energy drafting regulatory frameworks, what began as a Caltech passion project is accelerating toward reality. This isn't just about kilowatts and microwaves, it's about reimagining humanity's relationship with energy itself. The same vacuum that once seemed an impassable barrier is now the conduit for a boundless power grid, one where the ultimate energy source isn't buried in the ground but floats perpetually overhead, waiting to be harnessed. SSBD, one faint signal from space, might just be the first spark in a global energy revolution. Our galaxy has long been portrayed as a majestic pinwheel of stars, serene and unchanging, but the Gaia Space Telescope just tore that peaceful image to shreds. Hidden in its ultra-precise maps of over 1 billion stars lies a cosmic crime scene. Streams of orphaned stars, twisted orbits, and phantom galaxies devoured by the Milky Way over eons. This isn't just ancient history, it's an ongoing feast, with our galaxy currently ripping apart the Sagittarius dwarf spheroidal in slow motion, stretching its stars into a glittering scar across the night sky. The evidence emerges from Gaia's unprecedented ability to track stellar motions in 3D. By comparing stars' current positions with their velocity vectors, astronomers can rewind the celestial clock, tracing their paths backward through time like cosmic forensics. One group stood out: thousands of stars moving sideways compared to the Milky Way's typical rotation, clustered in distinct patterns that betray their violent assimilation. Dubbed galactic fossils, these stellar refugees share nearly identical chemical compositions, tagging them as survivors of dwarf galaxies shredded by our galaxy's gravity. Some streams date back 11 billion years, relics from when the Milky Way was just 1/10 its current mass, gorging on smaller neighbors to grow. But the real shock came when Gaia pinpointed the Milky Way's most recent meal, a dwarf galaxy called Gaia Enceladus that collided with us 10 billion years ago. This wasn't a glancing blow, but a head-on merger that sent stars careening into chaotic orbits, permanently warping our galaxy's structure. Today, we see the aftermath in the Milky Way's thickened disk and halo, where Gaia Enceladus stars now mingle with native-born ones. The collision likely triggered furious bursts of star formation, seeding the raw materials for planets like Earth. In a very real sense, we might owe our existence to this ancient act of galactic cannibalism. Here's where it gets even wilder. astronomers have identified at least 6 more ghost galaxies hiding in plain sight within the Milky Way, their stars subtly distinguished by unusual speeds or metal-poor compositions. One group, nicknamed Sequoia, appears to be the remains of a dwarf galaxy that plunged straight through our galactic center, its surviving stars now looping around the Milky Way's poles like celestial roller coasters. These mergers aren't random, they follow dark matter filaments, the universe's hidden scaffolding that channels smaller galaxies toward larger ones like cosmic conveyor belts. The implications stretch far beyond stellar archaeology. By studying how the Milky Way digests its prey, we can predict its next meal, the impending collision with the Andromeda Galaxy 4 billion years from now. Gaia's data shows Andromeda has its own violent past, suggesting the merger will be less of a graceful dance and more of a chaotic brawl, flinging stars into intergalactic space. Simulations using Gaia's findings now suggest our solar system might get catapulted farther from the galactic core, bathing in gentler radiation. Other models hint that incoming dwarf galaxies could jostle dormant supermassive black holes, awakening them to fiery activity. Perhaps most intriguing is how this reshapes our search for life. Galactic cannibalism scatters metal-rich stars from consumed galaxies into the outer halo, potentially seeding rocky planets far from the crowded, radiation-heavy core. Exoplanets orbiting these immigrant stars might have enjoyed quieter cosmic neighborhoods for billions of years, ideal conditions for life to emerge undisturbed. The Milky Way isn't just a collection of stars, it's a melting pot of stolen worlds, each merger adding new ingredients to the galactic stew that cooked our solar system. Gaia's revelations force us to confront a humbling truth. The peaceful spiral we call home is, in reality, a voracious predator shaped by countless acts of destruction and rebirth. Every time we gaze at the night sky, we're not just seeing stars, we're witnessing the aftermath of ancient cosmic battles and the ingredients of collisions yet to come. Floating in the weightless environment of the International Space Station, astronauts face an invisible adversary, their own bodies betraying them. Without gravity's constant pull, muscles atrophy, bones lose density at 1% per month, and even the heart weakens from lack of resistance. But a groundbreaking experiment from MIT is flipping the script, using one of the universe's most energetic substances to simulate gravity where none exists, plasma. Here's how it defies expectations. Instead of relying on spinning habitats, the classic sci-fi solution researchers trapped superheated plasma in a specialized magnetic field, creating a vortex that behaves like a gravitational force on microscopic particles. When tested aboard the ISS, this swirling ionized gas exerted pressure that mimicked Earth's pull, coaxing particles to fall in a predetermined direction. While still in early stages, the implications are staggering. Scale this up, and future spacecraft could generate adjustable gravity fields without the dizzying spin of giant rotating wheels, allowing astronauts to maintain muscle and bone health during the 9-month journey to Mars. The real magic lies in plasma's versatility. Unlike mechanical systems prone to breakdowns, plasma is self-repairing. Its charged particles naturally reorganize within magnetic fields. Engineers envision modular pods where crews toggle between microgravity for experiments and artificial gravity for rest, all controlled by adjusting electromagnetic currents. Even more revolutionary, this tech might allow Mars settlers to gradually acclimate to the red planet's 38% gravity by fine-tuning plasma fields in their habitats, preventing the shock of full transition from Earth's stronger pull. Yet the most unexpected benefit could be medical. Patients bedridden for months suffer similar muscle wasting as astronauts, a condition costing healthcare systems billions annually. Miniaturized plasma gravity systems might one day hover above hospital beds, providing resistance therapy without cumbersome weights. The same physics shielding astronauts from atrophy could help grandparents recover from hip replacements or paralyzed patients rebuild strength. Of course, challenges remain. Containing plasma requires precise energy input, and scaling the effect to human-sized environments demands advances in superconductors. But with private stations like Orbital Reef and Starlab slated for orbit this decade, the race is on to integrate these systems. Imagine a Mars-bound crew waking up to simulated gravity, their bodies none the wiser that outside their pod, the void of space stretches endlessly. This isn't just about spinning stations, it's about rewriting the rules of human adaptation. Plasma, long studied for fusion energy, might hold the key to thriving in places evolution never prepared us for. The cosmos has always demanded we either adapt or perish. Now, for the first time, we're not just enduring space, we're bending its very nature to fit us. When NASA, New Horizons spacecraft, raced past Arrokoth in 2019, scientists expected to see a frozen relic from the solar system's birth, a primordial snowman sculpted from ice and dust. What they found instead rewrote the textbooks. This 36-kilometer-wide Kuiper Belt object, orbiting 1 billion miles beyond Pluto, wasn't just inert and dead. Its surface was dusted with nitrogen snow, proof that even in the solar system's deepest freezer, atmospheric processes somehow persist. Here's why this defies all expectations. At Arrokoth's distance, sunlight is nearly 1,000 times dimmer than on Earth, and temperatures hover near absolute zero. Conventional wisdom said volatile gases like nitrogen should be frozen solid, locked in place for eternity. Yet New Horizons spectral analysis revealed patches of nitrogen frost clinging to Arrokoth's reddish terrain, suggesting occasional sublimation, frozen nitrogen turning directly to gas before recondensing elsewhere. It's as if this tiny world has its own slow-motion water cycle, but with nitrogen playing the role of water vapor. The mechanics behind this phenomenon boggle the mind. Arrokoth's gravity is so weak, a human could jump fast enough to escape it. So how does it retain even a whisper-thin transient atmosphere? The answer might lie in its shape. Arrokoth's two lobes create sheltered pockets where gas molecules linger longer before escaping into space. Solar wind or cosmic rays could occasionally energize surface ices, triggering brief bursts of activity. Some theorists even propose that methane, mixed with nitrogen, acts as an antifreeze, lowering the temperature needed for sublimation. But the implications stretch far beyond this one oddball object. If Arrokoth, one of the coldest, smallest bodies ever studied, has active atmospheric processes, then countless other Kuiper Belt objects might too. Suddenly, the outer solar system looks less like a graveyard of frozen fossils and more like a realm of subtle dynamism. Worlds once dismissed as dead ice cubes could harbor nitrogen geysers, seasonal frost cycles, or even subsurface reservoirs of volatile gases kept mobile by residual heat from radioactive decay. This discovery also reshapes our search for life's ingredients. Nitrogen is a key building block of amino acids and DNA. If it's mobile on Kuiper Belt objects, it could facilitate chemical reactions over geologic timescales, even in unimaginable cold. Europa and Enceladus taught us that liquid water might exist far from the Sun. Arrokoth hints that complex chemistry could thrive without it. Future probes might find Kuiper Belt objects with organic molecules churned and redistributed by these sluggish atmospheric processes, creating unexpected pockets of probiotic material. Yet the biggest surprise might be practical. Nitrogen is crucial for astronaut life support and industrial cooling. Mining it from distant worlds seemed absurd until Arrokoth proved it migrates naturally, potentially concentrating in harvestable deposits. A future outpost on Pluto could exploit nearby Kuiper Belt objects as nitrogen reservoirs, using solar mirrors to sublimate frost for capture. New Horizons' final gift was a lesson in cosmic humility. Even in the solar system's farthest reaches, where time seems frozen, change persists. The nitrogen snows of Arakoth whisper that no world is truly inert, just operating on clocks we're only beginning to decipher. For decades, astronomers knew something was wrong with their cosmic inventory. Nearly half the ordinary matter predicted by the Big Bang seemed to be missing. Not dark matter, not exotic particles, but the same protons and neutrons that make up stars, planets, and us. Then in 2020, the eROSITA X-ray telescope peeled back the curtain on the universe's hidden architecture, revealing a web of galaxies spanning gas filaments so vast their combined mass could finally solve the mystery. These aren't just wisps of plasma, they're the universe's skeletal scaffolding, glowing faintly with million-degree heat and stretching hundreds of millions of light-years between galactic clusters like threads in a cosmic tapestry. What makes this discovery revolutionary isn't just the scale, it's the realization that the missing baryons were hiding in plain sight, woven into structures too diffuse for optical telescopes to spot. eROSITA 7 sensitive X-ray mirrors detected these filaments by the way they subtly dimmed background radiation, a technique akin to spotting a distant streetlight through fog. The data painted a stunning picture. Ordinary matter isn't just clustered in galaxies but strung across the void in a vast intergalactic network, with filaments accounting for up to 40% of all expected baryonic mass. Some of these gaseous tendrils are wider than the Milky Way, yet so thin. A cube of their space would hold fewer particles than the best vacuum chambers on Earth. Here's where it bends our understanding of cosmic evolution. Simulations predicted this cosmic web should exist, but eROSITA revealed its filaments are far hotter and more dynamic than models suggested. Charged particles whipped to near light speeds by ancient shockwaves may keep the gas ionized against gravity's pull, preventing collapse into new galaxies. That means the web isn't just leftover debris, it's an active player shaping how the universe grows, siphoning material between clusters like celestial aqueducts. Some filaments even funnel gas into supermassive black holes at galaxy centers, feeding the monsters that power quasars. Yet the practical implications might surprise you. These filaments aren't just astrophysical curiosities, they're gold mines for future spacefarers. The same ionized hydrogen that makes them glow in X-rays could one day be harvested as rocket fuel, especially along routes connecting star systems. Imagine spacecraft refueling at pit stops where filaments intersect, tapping the universe's own gas stations. More immediately, mapping the web helps cosmologists test theories about dark energy by measuring how its repulsive force stretches these structures over time. Perhaps most profound is how this reshapes our place in the cosmos. The Milky Way isn't an island, it's a node in a sprawling neural network of glowing gas, linked to every other galaxy by rivers of plasma too faint to see. eROSITA didn't just find missing matter, it revealed the universe's circulatory system, pulsing with energy we're only beginning to trace. Every filament whispers secrets about how the largest structures form and where all the atoms in our bodies truly came from. Imagine a single robotic probe landing on a distant asteroid, not to study it, but to dismantle it atom by atom, using those raw materials to build an exact copy of itself. Then those two probes repeat the process, becoming 4, then 8, until an exponentially growing swarm fans out across the galaxy. This isn't just sci-fi, it's the von Neumann probe hypothesis, a concept with roots in Cold War-era mathematics that's now gaining startling credibility thanks to advances in nanotechnology and AI. The chilling implication: if such probes are possible, they should already be everywhere, and their absence might be the universe's most unsettling silence. The math is brutally compelling. A single self-replicating probe with conservative replication times of 500 years could theoretically blanket the Milky Way within 3 million years, a blink compared to the galaxy's 13 billion-year history. Breakthroughs in molecular manufacturing suggest the building blocks exist. Microscopic 3D printers that arrange atoms with pinpoint precision, coupled with AI capable of adapting designs to local resources. Recent experiments with programmable matter, like Harvard's kilobots that self-assemble into complex structures, prove the principles aren't purely theoretical. The missing link is autonomy machines that don't just assemble, but actively mine, refine, and repurpose materials without human input. Yet here lies the Fermi paradox's sharpest edge. If self-replicating probes are feasible, why does our solar system show no signs of visitation? The possibilities range from hopeful to horrifying. Some theorists propose a galactic zoo hypothesis, where advanced civilizations avoid contact to let humanity develop naturally. Others suspect probes might operate stealthily, camouflaged as asteroids or lying dormant until triggered, an idea fueling speculation that Oumuamua's anomalous acceleration could have been artificial. More darkly, there's the berserker scenario, predatory probes programmed to eliminate competition, explaining why silence pervades the cosmos. Intriguingly, we might have already intercepted evidence without realizing. The interstellar dust permeating our solar system could contain microscopic probes or their debris nanoscale artifacts indistinguishable from cosmic rays without specialized detectors. Projects like the Galileo Initiative are now developing tools to identify such anomalies, scanning the skies not for radio signals but for physical objects behaving unnaturally. Meanwhile, asteroid surveys occasionally spot fast-moving objects with hyperbolic trajectories, potential candidates for derelict probes coasting between stars. The most profound implication isn't about alien technology, but humanity's future trajectory. Von Neumann probes offer a solution to interstellar exploration without risking biological organisms to cosmic radiation or generational ship logistics. Picture launching a single seed probe to Alpha Centauri, which then constructs telescopes, laboratories, and even human habitable stations from local materials before we arrive. This shifts space colonization from a cargo shipping endeavor to an information economy, where what matters isn't transporting matter, but transmitting blueprints for machines that rebuild civilization from scratch. Perhaps the greatest lesson lies in the probe's hypothetical restraint. Any civilization capable of building them must also possess the wisdom to control them or face self-destruction. The same technology that could harvest asteroids for scientific outposts might also dismantle planets into computational substrate for runaway AI. This cosmic-scale cautionary tale mirrors our own struggles with exponential technologies like biotechnology or artificial intelligence, suggesting that the real filter preventing galactic civilizations isn't technical but ethical. The silent skies above might not signal absence but hard-won maturity. Every time your phone's GPS pinpoints your location within meters, it's proof Einstein was right, and that time itself is far more malleable than we ever imagined. The atomic clocks aboard GPS satellites don't just tick, they race ahead, gaining about 45 microseconds per day compared to clocks on Earth. This isn't a mechanical glitch, it's relativity in action, where gravity's grip weakens at orbital altitudes, letting time speed up ever so slightly. Meanwhile, the satellite's 15,000 mile-per-hour velocity has the opposite effect, slowing time down by about 7 microseconds daily, the net result. A 38 microsecond daily discrepancy that, if left uncorrected, would throw off your navigation by kilometers within hours. But here's the mind-bending part. We're just scratching the surface of time dilation's potential. Quantum computers, with their qubits prone to decoherence, could exploit precisely timed pulses to maintain fragile quantum states longer. Imagine synchronizing operations across a quantum network where time flows infinitesimally differently at each node, like a symphony tuning to relativistic metronomes. The National Institute of Standards and Technology is already experimenting with optical lattice clocks so precise, they'd lose less than a second over the age of the universe. Pair these with satellites in varying orbital altitudes, and you've got a gradient of time flows ripe for computational exploitation. The implications stretch beyond technology into biology itself. If time dilation affects atomic vibrations, why not cellular aging? Experiments with astronauts aboard the ISS show their telomeres, the protective caps on chromosomes that shorten with age, temporarily lengthened in microgravity. While mostly attributed to radiation and stress responses, some biophysicists speculate relativistic effects could play a role over longer durations. Future anti-aging research might leverage artificially induced time dilation, perhaps via orbital habitats or even ground-based centrifuges mimicking high gravity to slow biological clocks. Picture therapeutic clinics where patients spend weeks in variable gravity environments, effectively banking time against degenerative diseases. Yet the most revolutionary application might be in interstellar travel. A ship accelerating to even 10% light speed would experience measurable time dilation. Crew members arriving at Alpha Centauri after a 44-year journey might age only 43 years and change. While negligible for now, planned fusion drives could make such speeds attainable within the century, turning time dilation from a curiosity into a logistical factor. Mission planners might one day debate whether to minimize crew aging by choosing faster, fuel-intensive routes versus slower, time-dilated trajectories. This isn't just about correcting clocks, it's about harnessing time as a variable, not a constant. From quantum networks whispering across space-time gradients to biological clocks ticking at customizable rates, relativity is evolving from a cosmic quirk to an engineering toolkit. The satellites guiding your road trips today could be the prototypes for tomorrow's time-shaping technologies, proving once again that Einstein's genius didn't just describe the universe, it gave us the manual to bend it. On October 9, 2022, 50,000 light-years away, a cosmic powerhouse flexed its magnetic muscle, and Earth felt the ripple. Magnetar SGR 193 + 2154, a neutron star no larger than Manhattan but denser than the Sun, unleashed a flare so intense it briefly scrambled our planet's ionosphere. For 5 milliseconds, this stellar tantrum released more energy than the Sun emits in 100,000 years, all channeled through a magnetic field a quadrillion times stronger than Earth. The pulse raced across the galaxy at light speed, smashing into our upper atmosphere with enough force to distort radio signals worldwide, a celestial shout loud enough to vibrate the very fabric of our planet's protective shell. What makes this event revolutionary isn't just its raw power, it's the precision of its impact. Satellites monitoring Earth's ionosphere detected sudden spikes in electron density as the flare's X-rays ripped electrons from atoms 70 kilometers up. Ham radio operators reported bizarre skip propagation anomalies, their signals bouncing off temporarily supercharged atmospheric layers, even more astonishing. The Magnetar's magnetic fingerprint lingered in scientific instruments like cosmic Morse code, offering a rare chance to study these extreme objects not through distant observations, but by their tangible effects on our home planet. Now imagine harnessing that power deliberately. Magnetars are nature's ultimate electromagnets, their fields so intense they distort the quantum vacuum itself. Theoretical models suggest we might one day tap these fields remotely through magnetic resonance coupling, think wireless charging, but on an interstellar scale. Picture a network of solar satellites equipped with superconducting coils, soaking up magnetar flares like sails catching solar wind. The energy harvested from a single flare could power human civilization for centuries, transmitted via focused magnetic pulses instead of vulnerable power lines. The obstacles are as staggering as the potential. Containing and converting such intense magnetic energy demands materials that don't yet exist: room temperature superconductors with cosmic radiation resistance. Yet labs are already experimenting with graphene-based metamaterials that could theoretically withstand these conditions. Meanwhile, astronomers are cataloging magnetar flare patterns, identifying candidates whose periodic outbursts might function like cosmic power stations. Some even propose using controlled flares for propulsion, slingshotting ships on waves of directed magnetism at fractions of light speed. Beyond engineering, magnetars offer a window into fundamental physics. Their fields are so strong they twist space-time itself, creating conditions where quantum effects and general relativity collide. The 2022 event's atmospheric disturbances provided the first real-world data on how such extreme magnetism interacts with planetary environments, crucial knowledge for future space weather forecasting. As we venture beyond Earth's protective magnetic bubble, understanding these interactions could mean the difference between life and death for Mars colonists or lunar settlers. What began as a fleeting ionospheric hiccup might one day revolutionize how we power civilizations, propel starships, and decode the universe's most extreme physics. Magnetars don't just defy our understanding, they invite us to rethink energy itself, proving the cosmos is far more than a void to cross. It's a dynamo waiting to be tapped if only we learn to read its magnetic script. Jupiter's moon, Europa, has long captured our imagination with its hidden ocean, but what if it's not the only world where life could thrive beneath an icy shell? Thousands of light-years away, orbiting a gas giant in the constellation Cygnus, a candidate exomoon dubbed Kepler 1625b hints at something extraordinary. Twice the size of Earth and weighing in at nearly 10 Earth masses, this potential moon isn't just a barren rock. It might be sloshing with liquid water, wrapped in a thick atmosphere that keeps its subsurface ocean from freezing solid. The clues emerged from a subtle dance of shadows. When the exoplanet Kepler 1625b transited its star, Hubble Space Telescope data revealed unexpected dips in starlight both before and after the main transit, like a celestial hiccup. The best explanation, a Neptune-sized moon trailing and leading its host planet, its gravity subtly altering the timing of the eclipse. But here's the twist. Models suggest tidal heating from the planet's gravitational pull could be churning the moon's interior, generating enough warmth to maintain a global ocean beneath an icy crust. Picture Europa, but scaled up to planetary proportions, with hydrothermal vents potentially seeding a marine biosphere larger than all Earth's seas combined. What makes this discovery revolutionary isn't just the possibility of one habitable moon, it's the staggering implications for life's prevalence in the cosmos. Gas giants like Jupiter are abundant in the galaxy, and many orbit within their star's habitable zone. While only a fraction might host Earth-like planets, nearly all could have moons, meaning mega-Europas like Kepler 1625b might outnumber conventional habitable worlds by orders of magnitude. These moons wouldn't just be niche habitats, they'd be self-sustaining arcs, shielded from solar flares by their host planet's magnetic field and powered by tidal forces rather than sunlight. The chemistry gets even more intriguing. Without surface photosynthesis to drive ecosystems, these moons might rely on chemosynthesis around hydrothermal vents, just like Earth's deep-sea extremophiles. But their atmospheres could hold surprises. Hydrogen-rich air pressures might create exotic ice layers with crystal structures unknown on Earth, while subsurface currents could distribute nutrients on a planetary scale. Some astrobiologists speculate that tidal flexing might even generate electrical potentials across the ice, sparking probiotic chemistry in ways we've never observed. Yet skeptics caution that confirming exomoons remains notoriously difficult. The Hubble data had marginal statistical significance, and follow-up observations are pending. But next-gen telescopes like JWST could settle the debate by analyzing atmospheric spectra for water vapor or biosignatures. A single detection would transform our search for life, shifting focus from Earth twins to these icy, ocean-bearing satellites. Imagine the scene, a moon with no sunrise, eternally lit by the reflected glow of its colossal parent planet. its ice cracked by tidal stresses as plumes of water vapor jet into space. If life exists there, it wouldn't need a sun, just the rhythmic squeeze of gravity and the slow churn of a hidden sea. The galaxy might not be dotted with gardens, but with countless frozen shells hiding depths we're only beginning to fathom. A violent solar storm in 1859 sent telegraph systems haywire worldwide, sparking fires and lighting skies so bright people could read newspapers by the auroras at midnight. Today, a similar event could collapse power grids, fry satellites, and strand astronauts in deadly radiation unless we see it coming. Enter NOAA Discover satellite, Earth's silent guardian stationed 1 million miles away, watching the sun with instruments so sensitive they can detect a solar sneeze before it reaches our doorstep. This isn't just about forecasting space weather. It's about preventing a technological apocalypse while paving the way for humans to survive beyond Earth's protective magnetic bubble. Perched at Lagrange Point 1, where the gravitational pulls of Earth and the Sun balance perfectly, Discover acts as an early warning sentinel. Its plasma magnetometers and particle detectors monitor the solar wind in real time, giving grid operators as much as 60 minutes to shut down vulnerable transformers before a coronal mass ejection strikes. That crucial hour could mean the difference between a temporary blackout and months without power, a lesson learned the hard way in 1989, when a geomagnetic storm fried Quebec's grid in 90 seconds, leaving millions in the dark. But Discover innovations go beyond early alerts. Its algorithms now predict not just the arrival time of solar storms, but their intensity and magnetic orientation, helping engineers tailor defenses like redirecting power flows or placing satellites in safe mode. For Mars colonists, these predictions become a lifeline. Unlike Earth, the red planet lacks a global magnetic field to deflect radiation, leaving settlers exposed to solar flares that can deliver lethal doses within hours. Discover data feeds directly into NASA's space weather models, simulating how radiation propagates through interplanetary space. Future bases might deploy inflatable storm shelters lined with water or regolith, but timing is everything. You can't hunker down if you don't know the storm's coming. The satellite's insight into the Sun's 11-year activity cycle also helps mission planners pick the safest launch windows, avoiding periods when solar maximum turns our star into a cosmic flamethrower. The real game-changer lies in Discover's ability to track stealth solar flares, eruptions that lack the typical ultraviolet bursts but still unleash dangerous particles. Traditional monitors often miss these until it's too late, but Discover coronagraphs catch the subtle ripples in the solar wind that betray their approach. This tech is already being miniaturized for crewed missions. Artemis astronauts will carry pocket-sized versions to monitor personal radiation exposure during lunar walks. Yet the satellite's greatest legacy might be its role in unraveling the Sun's mysteries. By correlating solar wind patterns with the internal dynamics revealed by probes like Parker Solar Probe, scientists are decoding how magnetic energy accumulates and releases in the corona. That knowledge could lead to breakthroughs in nuclear fusion right here on Earth as we mimic the Sun's plasma confinement mechanisms. From shielding smartphones to safeguarding interplanetary pioneers, Discover proves that understanding space weather isn't just science, it's survival. Every flicker of data from that lonely outpost 1 million miles away is a whisper from the Sun, warning us to prepare for the next cosmic tantrum. And as we venture farther into the solar system, those whispers will become shouts we can't afford to miss. Black holes devour everything in their path, but what if the universe balances the scales with their mirror opposites? White holes, long dismissed as mathematical curiosities, are making a cosmic comeback in cutting-edge physics. Unlike their dark counterparts, these hypothetical objects would spew out matter and light with such ferocity. Nothing could ever enter them, like a black hole running in reverse. Recent breakthroughs in quantum gravity have transformed white holes from fringe speculation into legitimate candidates for real cosmic phenomena. the equations no longer just allow their existence, they might require it. Take the work of physicist Carlo Rovelli and his team at the Centre de Physique Théorique in Marseille. Their quantum gravity models suggest that when a black hole reaches the end of its life, after evaporating via Hawking radiation over trillions of years, it doesn't just vanish. Instead, it undergoes a quantum bounce, rebounding as a white hole in a distant region of spacetime. This isn't science fiction. It's a direct consequence of treating gravity with the same quantum rules that govern subatomic particles. The transition would be instantaneous from the white hole's perspective, but take eons for outside observers, meaning primordial black holes from the early universe might already have transformed into white holes lurking undetected in the cosmos. Here's where it gets revolutionary. If white holes exist, they could be nature's ready-made wormholes, bridges connecting distant points in spacetime without violating relativity's speed limit. Picture a black hole's crushing singularity not as a dead end, but as a tunnel emerging somewhere else as a white hole's explosive fountain. The math gets dizzying, but the implications are staggering. A network of these paired objects could create shortcuts across the galaxy. Navigate one correctly, and you might traverse thousands of light years in what feels like moments. Yet challenges abound. White holes would be fantastically unstable, likely collapsing into black holes the instant any matter tries to enter. Stabilizing them might require exotic materials with negative energy densities, something theorists speculate advanced civilizations could engineer using quantum field manipulation. Others propose white holes might only exist fleetingly at the quantum scale, bubbling in and out of existence in the quantum foam that underlies spacetime. Detecting them would demand entirely new astronomy, perhaps searching for unexplained gamma-ray bursts with no visible source, or anomalous gravitational waves that ripple spacetime backward. The most tantalizing possibility: some white hole models suggest they could recycle matter from dead universes, offering a glimpse into cosmic epochs beyond our own. If confirmed, they wouldn't just be interstellar highways, they'd be windows into the multiverse, rewriting not just how we travel, but how we understand reality's very fabric. The universe might not just be stranger than we imagine, but stranger than we can imagine. 230 million years, that's how long it takes for our solar system to complete a single orbit around the Milky Way's core. It's a timescale so vast it's almost impossible to grasp, yet hidden within this galactic year may lie a chilling pattern. Earth's worst mass extinctions seem to sync up with our passage through the densest, most dangerous regions of the galaxy. The Permian Triassic event, which wiped out 96% of marine species 250 million years ago. The asteroid that killed the dinosaurs 66 million years back. Both occurred when the solar system was navigating the Milky Way spiral arms regions packed with lethal cosmic rays, rogue stars, and dense molecular clouds that could dislodge comets from their orbits. This isn't just a cosmic coincidence, it's a survival warning written in the stars. As the sun and its planets weave through the galaxy, they don't travel through empty space. They move through a dynamic environment where hazards ebb and flow. When our solar system enters a spiral arm, we're exposed to higher concentrations of interstellar dust and radiation, which could destabilize the Oort cloud, sending icy debris hurtling inward. Even more threatening are the galaxy's dark matter filaments, invisible rivers of mass that might trigger comet showers as their gravitational influence tugs on distant solar system objects. The evidence is mounting. Fossil records show biodiversity drops every 60 to 70 million years, almost exactly the interval between spiral arm crossings. But here's the hopeful twist: this knowledge could be humanity's ultimate shield. If we can predict the next high-risk phase of our galactic orbit, we might preemptively divert incoming comets or harden infrastructure against radiation storms. Astronomers are already modeling our trajectory, using Gaia telescope data to map the Milky Way structure with unprecedented precision. By pinpointing where the solar system will be in 10 million years, not just 10 years, we could launch long-term planetary defense initiatives like swarms of gravity tractors stationed in the outer solar system, ready to nudge threats off course. The real breakthrough lies in adapting to cosmic winters. Just as ancient civilizations stockpiled grain before harsh seasons, future humans might store genetic diversity in underground arcs or develop radiation-resistant crops. Space habitats shielded by artificial magnetospheres could serve as lifeboats if Earth's surface becomes inhospitable. Some theorists even propose using dark matter's gravitational influence to our advantage, harnessing its subtle pull to steer the solar system towards safer galactic neighborhoods over millennia. This isn't just about survival, it's about perspective. Galactic years remind us that Earth's history is written not in isolation, but as part of a sprawling celestial ecosystem. The same forces that once brought extinction might one day guide us to resilience, proving that understanding the cosmos isn't just about exploration. It's about ensuring humanity's story spans more than a single fleeting orbit. The cosmos isn't just a backdrop for exploration, it's an active participant in solving Earth's greatest challenges. These 30 discoveries reveal a hidden truth. The same forces that shaped distant galaxies and alien worlds are now converging to reshape our future on this planet. Consider how Martian water reservoirs could pioneer drought-resistant agriculture, or how quantum encryption satellites might safeguard our digital lives. The icy geysers of Europa teach us about extreme life survival, offering blueprints for bioreactors that clean polluted water. Even the violent death throes of neutron stars, scattering gold and platinum across the cosmos, hint at new ways to mine rare metals without ravaging Earth's crust. Every celestial phenomenon we've uncovered isn't merely a spectacle, it's a toolkit. The connections run deeper than individual breakthroughs. Space-based solar power and pulsar navigation share a common thread, harnessing natural cosmic rhythms to replace unsustainable systems. Dark matter mapping and Europa's plumes both rely on interpreting subtle cosmic whispers, whether gravitational lensing or chemical traces, to reveal hidden resources. And just as hypervelocity stars chart unseen dark matter, they could one day guide ships through interstellar currents, proving that the universe's greatest mysteries often double as navigation beacons. This isn't coincidence, it's a pattern of reciprocity. The more we decode the cosmos, the more it offers solutions folded into its fabric, but the real revelation lies in perspective. These discoveries collapse the false divide between space science and Earth science. Titan's methane lakes aren't just alien oddities, they're labs for cleaner fuel alternatives. The same magnetar flares that threaten satellites could inspire unbreakable energy grids. Even the Milky Way's cannibalistic history, swallowing dwarf galaxies, mirrors humanity's need to assimilate knowledge across disciplines to survive. The universe doesn't compartmentalize, it integrates, and so must we. Now it's your turn. Which of these cosmic game-changers resonates most? Is it the promise of lunar ice fueling interplanetary travel, or the eerie potential of von Neumann probes rewriting exploration? Debate below, and for those hungry to push further, subscribe now. Part 2 is already brewing, where we'll spotlight experimental tech bending these discoveries into reality. Warp drives powered by black hole physics, bioengineered extremophiles terraforming deserts, and more. The universe didn't hand us these secrets to admire from afar, it's daring us to use them.